This section introduces the theorem that connects derivatives, antiderivatives, definite integrals, and accumulated change. It is the bridge that saves us from evaluating every integral with a Riemann sum, because even calculus knows when a shortcut is deserved. These objectives move from computation to interpretation and application. By the end, you will be a master at calculating net change for a function you know the rate of change for. Riemann sums define the definite integral, but using them every time would be painfully slow. The fundamental theorem replaces an infinite rectangle project with two endpoint substitution and subtraction, which is the kind of efficiency we all dream about. Differentiation and integration reverse one another. For example, if you have population as a function of time, you can figure out how fast the population is changing using differentiation. And if you have the rate of change of population, you can figure out the net change in population using integration. Part 1 says the rate of change for an accumulation area function is the integrand evaluated at the moving endpoint. This is because it can be shown that how fast this area is changing at any instance x is exactly equal f of x. Part 2 turns a definite integral into an upper endpoint value minus a lower endpoint value. Two substitutions and a subtraction replace infinitely many rectangles, messy calculations with sigma and dreadful limit evaluations. It's the ultimate calculus shortcut. The evaluation bar means upper value minus lower value. Parentheses around the lower value are essential because a missing pair of parentheses can ruin a solution faster than a missing alarm can ruin an 8:30 class. The integration constant cancels between the endpoints and thus disappears from the final answer. The trapezoid formula produces the same area, so the calculus and geometry agree. It is always reassuring when two branches of mathematics confirm each other's answers instead of starting an academic rivalry. The function stays positive, so its integral is its area. The lower endpoint produces a negative value, and subtracting it increases the result. Both substitution methods are correct, but the variable and limits must match. Mixing u with x limits is like submitting the right assignment to the wrong course. Impressive effort, unfortunate result. The inside expression x squared plus 1 is the natural substitution because its derivative supplies the x factor. The limits also change immediately, using this inside expression. Once the limits are converted, there is no need to return to x. The entire calculation stays in u. The fundamental theorem requires continuity throughout the interval. Here the interval crosses 0, where the function is undefined, so using part 2 of the fundamental theorem here is much like ignoring a missing prerequisite and hoping registration does not notice. Integrating a rate of change gives the net change, and adding that change to the initial amount gives the final amount. It is a dependable formula, unlike calculating your final grade using optimism as an extra credit category. Because the rate was measured in hundreds of people per year, the integral is measured in hundreds of people. Rounding at the end is essential, because 7/10 of a person would be a murder case. A marginal function is a derivative, so integrating it recovers a change in the total function. In business calculus, marginal does not mean unimportant. It simply means rate of change. The integral gives $5,000 of variable cost, and the fixed cost must then be added. The fixed cost can't be ignored, much like your monthly rent, which you have to pay even if you wear away the whole month. The interval starts at 200 because we want only the additional cost beyond that level. The wording determines the interval, and the interval determines which change is being calculated. Reading carefully is part of the mathematics, despite generations of students insisting that calculus should not contain surprise English questions. Marginal revenue gives the rate at which total revenue changes as sales increase. The toaster ovens may be deluxe, but the calculus remains standard edition. Because selling 0 ovens produces 0 revenue, the integral from 0 to 200 gives the total revenue directly. Apparently, the revolutionary business principle here is that selling nothing earns nothing. Integrating the hourly assembly rate gives the total production over 4 hours. We need to round to the nearest whole number in a case like this. The exponential rate integrates to a total of about 172.62 thousand kilowatt-hours. The units confirm the interpretation, while the electricity bill confirms that exponentials have expensive taste. Increasing the upper limit from x to x plus h adds a thin strip of area. For small h, the strip behaves like a rectangle, one of the few approximations that gets promoted to an exact theorem after taking a limit. The blue region is the accumulated area to x, and the red strip is the extra area gained by moving to x plus h. The strip is narrow, and the narrower it is the better it can be approximated as a rectangle. As h approaches 0, the thin strip approximation becomes exact, producing a prime of x equals f of x. The limit turns an approximation into an exact value, namely the instantaneous rate of change of the area. Part 1 lets us differentiate the accumulation function immediately. Replace t by x in the integrand. No integration is needed, making this one of the rare calculus problems where doing less work is mathematically responsible. Evaluating a at 3 gives the accumulated area from 1 to 3. At x equals 1, the interval has 0 width and therefore 0 accumulation, much like a study session scheduled from 2 o'clock to 2 o'clock. The fundamental theorem connects accumulation, derivatives, and endpoint evaluation. It turns the definite integral into a practical tool, which is good because infinitely many rectangles were beginning to create a serious storage problem. The theorem shows that integration and differentiation are inverse perspectives on change.